All right. So today we're gonna have Dan Green from University of California, San Diego, at one before the last talk of the semester, who will be telling us about cosmic surveys and the quantum universe. Thank you so much for your time, Dan, and please.
Well, thanks for having me. I was a little unsure about the level, so it'll probably vary from maybe too simplistic to too technical at various points. So please stop and interrupt me if I lose you or something's not clear.
Yes.
Everything good there?
That's maximum. Should we stick with this speaker or should we change the speaker? That's good.
Let's see. Switch to.
Let's switch to the. I think that. Can you say one more thing?
Hi, how's it going?
All right. Good.
Is it working?
Yes.
Okay. Okay, so today I'm going to talk to you about kind of two very different topics that are related and that hopefully will become clear, which is understanding the quantum nature of the universe and the implications for cosmic surveys of big classical objects like galaxies. So the plan for the talk is I'm first going to introduce this subject of quantum cosmology and why you may or may not care about it. This will lead us to talk about dimensions of quantities associated with these maps. I'll then use this to prove some results about the properties of these maps using the positivity of Fisher information. And then we'll talk about how that manifests itself in things we can observe through galaxy surveys. So when we look at the universe, we're usually talking about maps like this, like we take a telescope, we look out and we see big objects like stars and galaxies and clusters of galaxies, or perhaps the cosmic microwave background, which is sound waves the size of the entire universe. And so when you think of cosmology in terms of these kinds of objects, you wonder why people would think of a subject of quantum cosmology as being particularly interesting. For one, it's not totally clear what you should even think of in terms of quantum mechanics when you are part of the system and we're part of the entire universe. And it's still totally unclear how to make sense of what we observe in terms of sort of rigorously defined quantum observables in this sense. More practically, and cosmologists tend to be pretty pragmatic, you might think we're looking at these giant classical objects, and I'm studying the statistics of them. Why do I even care about whether there's some underlying quantum description? What I'm looking at is a purely classical observable. Now, I would say that most of these questions are still basically unanswered. We don't know really how to think about quantum mechanics of the universe as a whole, but it's very likely that it does matter to our universe. And the reason is because observations we have suggest that the universe, both in the past in terms of the physics of inflation and the future in terms of the dark energy dominated universe we observe today, are described by accelerating cosmologies. And in the picture of an accelerating cosmology, the quantum turns into the classical through the expansion of the universe. So we have things that look like quantum mechanical bubble diagrams, for example, that through the expansion of the universe get turned into, honest to God, the density fluctuations that any classical or quantum mechanic would define as a real thing. The origin comes through the sort of exponential nature of the expansion. So just to define some variables that are familiar to cosmologists, we usually think of the expansion of the universe as being described by the evolution of some scale factor I call A of t. And in these exponentially or nearly exponentially expanding spacetimes, the scale factor and hence physical distances grow exponentially in time. And for a good approximation, we'll think of the rate of that exponential being the Hubble parameter as being close to constant. Now, this process of taking things that are close together and stretching them until they're exponentially far apart produces noise in the fluctuations of objects. And the amplitude is typically controlled by this parameter, the Hubble parameter. So the Hubble parameter plays all of the important physical role, a role of defining scales in one of these accelerating cosmologies. Now, what the picture looks like in terms of waves, which are what describe the sort of individual quantum mechanical variables is that through the expansion of the universe, we say start with very short wavelength waves that through expansion get redshifted to very long wavelength waves, and they kind of cross from being sort of quantum vacuum fluctuations when they're small compared to the scale of curvature to being large compared to the scale of curvature. And this was calculated by many people back in the 80s in the context of the theory of inflation. And now coming back to quantum cosmology, it makes sense to think about quantum cosmology when we're thinking about these fluctuations, when we're thinking about sort of the waves and what they do in the expanding universe. So in most practical contexts, we're not thinking about the wave function of the universe as a whole, but instead we think of the wave function as being built out of a single classical background and then a quantum wave function defining the evolution of these fluctuations on top of this fixed background. This strategy works extremely well and has been used to make predictions for all kinds of observables that are being tested with cosmic data. So this procedure makes sense when the fluctuations are small, and we can really think of the split of the background into classical plus quantum. In terms of, say, the transverse traceless gravitational waves, we have some amplitude for those fluctuations that our theory predicts. The dimensionless amplitude is basically set by a ratio of Hubble to the Planck scale. And so this is much less than 1 under the usual set of assumptions, which are that, the curvatures are small in Planck units, and therefore semi-classical gravity is under control. So from this point of view, like a typical just dimensional analysis even, you would say, well, as long as H is small, I am totally comfortable doing this split into background plus fluctuation, and everything should be fine. Now, the problem is that that's not how things work out in a lot of other calculations. So it tends to actually be true, surprisingly, for perturbative calculations of the metric. But if I just take a generic field in de Sitter and I calculate, say, like a 2-point function, we'll find two types of behavior which are very worrisome if you think the way that you're going to make sense of quantum gravity is through just keeping fluctuations small. The first are sometimes called secular divergences or secular terms. It's basically that these 2-point functions tend to grow linearly in time. And so after a certain amount of time, no matter how small you make h, these things will become as large as you like. The second kind of divergences are just infinity, and infinity of the kind that that are not UV divergences, but are IR divergences. So things that we don't know how to renormalize. So they're not infinities that we know how to absorb into a set of couplings, but there's some other kind of infinity that similarly causes you concern if the way that you think you're going to manage perturbative, making sense of a quantum universe is through keeping quantum mechanical fluctuations small.
Question?
Yep.
So usually like when we say 2-point function, it's like inverse distance.
Sorry, can you repeat the question?
We talk about like 2-point function, it goes inversely as a distance between the 2 points. And if like distance is increasing, shouldn't the 2-point function vanish at last time?
So this one here is for a massless field. So here, this is just literally the answer for massless field. Massless field, the actual power law is like a log. It's not like it's like a log CFT. Like it doesn't have correlation functions that vanish, finite separation, and that's related to the statement that it gives scale invariant correlators. In other cases, this will be a correction to a power law. So you'll have a power law that's like some fixed separation of the distance, but then it will grow with corrections that go like log of t. So I don't know, does that answer the question?
Yeah, okay, thank you.
I'm being somewhat schematic here, but I'll hopefully be more precise as we go on. Okay, so the interpretation of this result was given by Starobinsky and Vilenkin in the early 80s. So they saw this 2-point function here. This is like this is an equal time single point 2-point function. So it's like phi squared at a single point in space. Like it's not a finite separation 2-point function. They find this thing grows linearly in time, and they say that looks like a random walk. So if I saw a 2-point function, if I told you I have a variable that's a statistical variable, and its absolute value squared grows linearly in time, you say, oh, I know what that is. That's what the sum of a bunch of random numbers. And as I add more and more random numbers, the variance grows linearly in time. And so their intuition is, imagine if I sat at a single point in this space as modes continually freeze out, then I will see this kind of, because the phase of these waves will be random, I will see a sort of random walk at that point. So as I add up more and more waves, I will see that the local value of the scalar field evolves according to a random walk, hence giving me this linear in time growth. Now, so then they said, look, like you can put that together back with an interacting picture where this scalar field may evolve on some potential. And so there's a contribution to the evolution of the scalar field, which is just this random walk. But then, of course, there's the force of the potential that brings it back towards the origin by just the classical forces. And I can put those two things together in the form of a Fokker-Planck equation, where the time evolution of the probability of finding this scalar field, again, at a single point in the universe, evolves according to a diffusion term, that's the quantum noise, and a classical term, which is just this constant drift. And together, they give rise to an equilibrium distribution as you wait long enough. So instead of this probability, the probability of finding x diverging as t to infinity, it instead finds some finite, it settles into some finite set of values. This probability distribution is under control. And while the field evolves to some large values in terms of the coupling, that's not necessarily problematic on its own. Now, this has some nice properties. So stochastic inflation resolves some of the obvious confusion. So it gives an interpretation for this divergence with time and actually resolves it, making everything finite. It also removes some of these infrared divergences that people had worried about, although the reasons for that, again, were not known. They're just, this is a differential equation we can solve, and it seems to give finite answers. The problem is that the derivation of this was very schematic. I observed that a 2-point function grew linearly with time, and then I decided that the right way to think about that was in terms of a differential equation that I seem to get from nowhere. That might cause you some concern. Some other concerns are that if you apply this set of equations to massive fields, so not just light fields, but fields that have a large mass, eventually you can just check that it doesn't agree with the full quantum field theory predictions, although it does do a good job for the predictions of light fields. It also doesn't explain other kinds of divergences that have been found. So this explains the resolution to the divergences of massless fields, but there are actually other kinds of linearly diverging things with time or IR divergences associated with heavier fields that, again, are not explained by this kind of random walk picture. And so even though this is suggestive of a kind of strategy to make sense of what's going on in our universe and universes like it, we still, just this picture is missing sort of some core feeling that you've actually understood the problem. Okay, are there questions so far?
So what was the principle for, how did they argue for that differential equation? It's just like some qualitative, I mean.
So it's a combination of two things. It was an inspired guess based on the amplitude of the noise and just the fact that any such equation should have a classical force term. Like, this is a well-known equation. The second one was that Starobinsky specifically had a kind of like integrating in picture. So he really said, like, if I thought of this like as a, like, what's the value of a scalar field at a point, and I bring one mode across the horizon, how would that change? So it's a kind of RG-like picture, and we'll talk about exactly how this is derivable from RG. It kind of had this, like, if I had a window function that separated the modes outside the horizon from the modes inside the horizon, it feels like you should add a mode as you do one time step. And so he had a kind of derivation of this equation that was kind of RG-like from just thinking about the influence of that one mode crossing the horizon, but we will do a better job. So like it's a guess that turns out to have, again, when people guess the right answer, it's very hard to be like, well, how did you know to guess the right answer? It's like, what's the right answer? Of course, that's how I thought about it.
Description, derivation of this equation. Is that right? They offer
Not from quantum field theory, not from quantum field theory. So it was kind of like a semi-classical picture of thinking. So the idea was, let's think of the modes crossing the horizon like a random walk. And then how I would think about what happens as every mode crosses the horizon. Well, I would say, okay, well, every mode is drawn from a Gaussian distribution that has an amplitude of variance h. And so every Hubble time I get a new mode, and that mode has, so it was very like, it was kind of like classical in essence, with a sort of like quantum added on, just as the like, this is how you should think about the modes crossing the horizon. But there was not a quantum field theory derivation. However, what was shown by Starobinsky and others in the early 2000s was that for certain non-trivial calculations, they could take the answer that came from just solving this equation and using it to calculate higher point statistics, and then comparing those to direct calculations of higher point statistics and showing that they reproduced the leading behavior. So they were basically getting the right answers to non-trivial calculations from this equation. So it was kind of known that it worked, but the derivation, like you start from quantum field theory and you land at this equation, did not exist. Does that answer your question?
Yeah, it's just very confusing for me to, I mean, quantum mechanics could not be reduced to probability distributions, right? There's interference, there's all sorts of things like that. So in what regime did they even speculate that the equation of this type would hold?
Yeah, so again, they're working in the super horizon limit with the idea that quantum mechanics doesn't matter there. So yes, but we'll come back to in what sense. There's a very precise sense in which quantum mechanics is irrelevant to this equation in the RG sense, like it's a technical version of irrelevance. But yeah, it's a totally reasonable question. Again, this was not derived from anywhere. It just, I mean, it was inspired, but we'll, yes. But yeah, we'll see where it comes from. So hopefully you'll be happier as we go. Okay, so the way that we're going to think about this is again, so of course, if you're happy with CFTs and quantum field theory and anomalous dimensions, you'll be perfectly fine with this. But we're going to find our theories aren't unitary, so I'm going to instead use a more statistical way of thinking about what we're after. So the familiar context for anyone of how you get funny scaling behavior is a fractal. So we're going to find that a lot of this behavior we can think of as kind of a fractal dimension for a lot of objects relevant to consider. So fractal dimensions can be defined in like simple examples like this cove triangle, where you say that the meaning of the anomalous dimension here is basically how many line segments do I need to include as a function of the depth of this fractal. So as I break the fractal into smaller and smaller pieces, how big does this fractal get? So in the cove triangle, you basically take every line segment, divide it in 3, and put in 4 and put in 4 line segments in its place to form this kind of like star-like pattern. And you do that sequentially down. So every time you divide the scale of the system by 3, you increase the size by 4. And so because of that, the way to think about the scaling behavior of this system is that it has an anomalous dimension, or a dimension we'll call delta, which is log 4 over log 3, which just captures this fact that when I change the size of the system by a power of 3, I actually change the number of line segments by a power of 4. Now, if we were to take this system and say, okay, let's think of this as being kind of like a normal line plus some correction, then the normal line has a linear relationship between the physical scale and this depth. And so if I were to add this correction, it would look like something that goes like this change to the power law plus something proportional to the log of the physical size of the system. And so of course, we know how to resolve such logs. This is not, of course, not small. Gamma times log n0 is arbitrarily large as I take the system large. But of course, we all will recognize that this is an example of RG flow. And so we would just say, okay, look, like we know we're supposed to resum this into a pure power law. So in cosmology, the linear in T is not obviously like that. But if you think linear in T is not reflective of linear in time, but is a log of the scale of the system, then we start to think of this as being very much like something we'd recognize from a fractal. So here, physical scale of our system is growing exponentially in time, so logarithmic corrections to the scaling behavior will show up as things that grow linearly in T. And so in this way, we're going to think of all of these funny factors that are linear in T as having some relationship to anomalous dimensions or anomalous scaling behavior. Okay, so let's come back to this picture. We're going to think about how to organize our ideas on the long wavelength in terms of these scaling behaviors. Okay, so again, we have this picture where in physical distances, we have these physical wave numbers that are getting redshifted. So over time, the wave numbers become small or the wave lengths become very large compared to the curvature scale of the problem. However, it's sometimes more convenient to use what's called co-moving coordinates. So here, because we will work with sort of flat spatial slices, we can think of Fourier transforming in distances at fixed wave number, and instead it's the size of the universe that's changing. So the curvature scale in co-moving coordinates is getting smaller while the wave numbers are staying constant. These are, of course, equivalent points of view, but this one is calculationally slightly easier because it means that scalings with distances don't change in time. There's just time evolution we need to worry about. So then what we want to do is we want to think about how do we organize the degrees of freedom of this theory that in the limit where the wavelengths are all very long. Again, we're trying to understand the long wavelength behavior of a quantum universe directly. And so rather than starting inside the horizon, solving a bunch of equations, getting a bunch of Bessel functions, and then Taylor expanding them directly, we're just going to start with the behavior at zero wave number, infinite wavelength. Okay, so you can the evolution of a scalar field in this universe follows this differential equation, and you can solve this differential equation when k equals 0 quite easily, and you find two power laws. These power laws, of course, look very familiar if you're used to working in ADS as well. You'll get an answer which is d over 2, which in this case is 3 spatial dimensions, minus nu, 3 over 2 plus nu, where nu is this expression in terms of the mass in Hubble units, and this factor d over 2 squared. Okay, so in cosmologist speak, though, these are two power laws. One of them we call the decaying mode, or the growing mode, but it actually still decays. This is for any positive mass, still negative power of growth, but it grows, it decays less quickly than the decaying mode, which goes like 3/2 plus nu. Now, the strategy we're going to use is to eliminate the time, is to make the time evolution explicit. So what we're trying to understand is the scaling behavior with the growth of the system. And rather than burying that inside of some asymptotic behavior of a Bessel function, we want to pull it out so that we can see with our eyes what's happening as this universe becomes large. So we replace the scalar field, we just make a nonsense, it's just a change of variables. We replace the scalar field with, we pull the time dependence directly outside, and we promote these things, these constants in our two new fields. So we have two fields. When I do this, these phi plus and phi minus become scaling operators. So they behave like operators of dimension alpha and beta. It just said my internet's unstable. Can you guys still hear me?
Yeah, you cut out for a second.
Okay.
That's okay.
Okay, I don't know what's going on. Okay, so you should think of phi plus and phi minus as being operators of dimension alpha, 3/2 minus nu, and beta for phi minus, 3/2 plus nu. In the limit, the mass goes to 0. this square root becomes 3/2 and alpha goes to 0. So important to remember, for a massless field, this thing is going to have be like a dimension 0 operator. This will be like a dimension 3 operator. And then we'll talk about the other cases in a second. Now, it's useful to think about this because, again, these powers are always going to come together. The power of scaling with distance associated with this operator always comes paired with the power of the time evolution, because of course the two come together to give physical distances. So the physical distance is the scale factor times the co-moving distance, and the physical wave number is the co-moving wave number divided by the scale factor. And so we'll find that these things always have to pair up, but doing it in this way makes it very clear what's going on in the system. So with this behavior, if we were to calculate the 2-point function of a scalar field at separated points but equal times, we'll find that the answer has to go like 1 over the distance squared to the power alpha, which is what you'd expect for an operator with that scaling dimension. And in fact, if you take the case of pure de Sitter, and you take the isometries of that spacetime, then the isometries act on these operators phi plus and phi minus exactly as if they are primary operators in a CFT with dimensions delta plus and minus, which are alpha and beta in our case. Now, in general, there's two kinds of free fields in de Sitter. There are fields that are often are called complementary series fields. These are little light fields, the ones whose masses lie in the windows 0 to 9/2 Hubble, or 9/4 Hubble. In this case, alpha is less than 3/2, and then the massless limit goes to 0. And beta is just this complement, 3 minus alpha. There's also the heavier fields, which are called the principal series. This is when the mass is greater than 9/4 Hubble squared. In this case, that square root becomes, the argument inside the square root becomes negative. We should pull out a factor of I. And now alpha and beta are 3/2 plus and minus I times I nu. And so alpha and beta are related by complex conjugation. So pictorially, this is what the space of fields of scalar fields in de Sitter looks like. We have our complementary series fields that are related by reflection around the line. The dimension equals 3/2. And then we have the principal series fields that are related by reflection around the real axis. That is complex conjugation, but always lie along this line, 3/2. Now, of course, we're not restricted only to the fundamental field. We can, of course, make composite operators. So if we take the complementary series, we can take phi and phi plus squared, phi plus cubed that have dimension alpha, 2 alpha, 3 alpha. We can combine phi plus and phi minus. So phi plus and phi minus has dimension 3, or just the phi minus squares. Similarly, we can do the same thing on the principal series, but now the principal series we see splits up in this way. Every level, they are related by complex conjugation, and they move by sort of powers of 3/2. So they go, the real part goes 3/2, 3, 9/2, etc.
Question?
Yep.
Sorry, usually here is where I start getting confused. All these statements are representation theory statements. There's no Hilbert space here, right?
Correct. There's no okay. Well, so in the free theory, it is claimed that so technically speaking, when people classify operators in this way, they're not actually classifying fields. They are usually classifying states. And the statement is that the unitary states, so here I'm saying in a free theory, this is true. Now, if you were to, instead of talking about a free theory, say, what is my rules for the list of unitary states, you would find the same conclusion. You would define states by eigenvalues under these symmetry operators. They would be defined by some deltas, and then the rules for unitarity, specifically that it has a norm that is real and positive, forces it to either lie here or lie along this line. Okay, now this is very important. This will be extremely important in a second. Okay, so you're right to be confused, and in particular, there will be no state or operator correspondence in this theory, away from the free theory. So it's important that although you see a lot of things that look like CFT, a lot of CFT intuition and even proofs of things that you know and love secretly, if not explicitly, use the state operator correspondence. And we immediately have to reject the idea there's state or operator correspondence. And if you accept that there's no state or operator correspondence, you'll be less confused as we go along. But there's, technically speaking, always a set of unitary states that lie along this line.
Sorry, my question is this: away from the free theory, is there a Hilbert space that you were talking about? Or
People
is it
do
just
define a Hilbert space. People define a space of states that they say can be used to resolve the identity, and that those states are perfectly good for making sense of calculations. They can do a Calvin-Lehman representation and reproduce actual answers that you calculate in different ways. So to the degree that you would like to say this Hilbert space that lives along this line, that has a continuous parameter space, exists, even though we'll see no operator creates a single state. And that's going to be the source of some confusion. But technically speaking, if you accept these states exist and you put them inside a correlator function, correlation functions to resolve the identity, it works okay. Does that help?
Yeah. So maybe we could come back to this at the end. I think my confusion is somewhat philosophical. When I say representation theory, we're talking about a vector space and a bunch of transformations. When we talk about the Hilbert space, we have in mind a bunch of operators that act on the vacuum and create states. You're telling me that the second doesn't hold?
No, yeah, the second does not hold, absolutely.
What I mean
well, again, it holds in a trivial mathematical sense, but not in a sense that you would like. So maybe that's a more useful statement. Like, people definitely construct these states and give them rules and they can apply, but a single operator always creates a continuous family of states. And so there's no, like, I take an operator, act on the vacuum, and I create a state. It always makes an infinite number of states. And so at some point it becomes pointless. But I'll try to explain where that statement came from concretely.
Thank you.
Okay, so now you have these composite operators. Okay, you can certainly, within the perturbative framework, start calculating things like anomalous dimensions, because of course you should expect such things to arise. And so indeed, you can go and say, I take the operator phi plus to the n, it's some nice scaling operator. But of course, if I take an interacting theory that has like a lambda phi to the fourth interaction, I can calculate the 2-point function of those composite operators. So involving this kind of two-loop looking diagram, you'll find that this generates a log, and that log should be interpreted as an anomalous dimension that should be resummed. Now, if you're not totally happy with the statement that it can be resummed, the easiest way to convince yourself that you better do this is you can take the case where this field is a conformally coupled field, and therefore the answer for whatever this anomalous dimension should just be the conformally mapped anomalous dimension of lambda phi to the 4 and d minus however many dimensions you like. And that corresponds in this case to this variable being a half, and you recognize this anomalous dimension being lambda over 16 pi squared as a flat space anomalous dimension for lambda phi to the 4 for the operator phi squared. So now you can, again, apply this to all kinds of masses and get this continuous curve that shows you the anomalous dimension of this operator. So everything seems to follow your standard rules. Okay, so in that regard, you would say, okay, look, like, what would I expect to happen? You would expect, okay, I take these operators, they had some free field values of alpha and beta, but of course, in some interacting theory, they should move around according to anomalous dimensions. And so the first such calculation was done by Marloff and Morrison, who did a fairly brute force and technically challenging calculation, and showed indeed that the interesting behavior is that these operators specific, so these operators, the complementary series, move around, and maybe you don't lose so much sleep over them just moving along this line. But what is particularly interesting and will be the subject going forward is that the principal series moves off the line. And that is not obvious, in particular because the fact that they lived on this line or we had these properties of reflection around this line was very important to understanding the sort of Hilbert space structure in some cases, or just, as we'll see, making sense of unitarity in these series. Okay, now, before we get to this pattern, we can talk about the pattern for alpha to again see that but thinking in this way is actually very useful, even if it is not totally obvious. So specifically, let's think about the light scalar, where we take the mass to 0 or alpha to 0. So in this case, now we have an issue of degenerate perturbation theory, right? So all of the operators phi to the n, when alpha was not 0, they had dimensions n times alpha in the free theory. So they're all nicely separated. But when you take alpha to 0, this infinite tower of operators all becomes degenerate. And when operators become degenerate, you shouldn't think of them having individual anomalous dimensions, but instead you should think of them as mixing via a matrix of anomalous dimensions. Now, what's peculiar is that because this is a dimension, these are all dimension 0 operators, it is an infinitely large matrix corresponding to any phi to the n being able to mix with any other phi to the n. Now, you can go and just start calculating elements of this matrix. And so there's a divergence that already happens just from Wick contraction in the free theory that gives you a mixing between phi to the n and phi to the n minus 2. You can also have, just through the evolution of the potential, there's a term that comes from phi to mixing in lambda phi to the 4 that looks like phi to the n mixing with phi to the n plus 2. And because this equation holds for all n, you can actually show that this equation can be derived from a master equation, assuming they all were classical statistical variables that came from the following probability distribution. Is that a question?
Yeah, in the first line, the dot, 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 these are all equal time correlators.
So so technically speaking, this derivation was held just ignoring the dots, and they're just single point endpoint functions however, you can insert the other operators that they're correlated with, but the phi to the n's are all at the same point in space and the same point in time.
Ah, okay.
So this is just think of this as a Callan-Szymanczyk equation for, again, Callan-Szymanczyk is useful for solving things when it's low point statistics, but technically applies as a statement to the operators inside any correlator. The same is true here. But for the individual one-point functions of these composite operators, this equation becomes stochastic inflation plus corrections. So in particular, that we now have control over how to calculate those corrections because it's just calculating this matrix of anomalous dimensions. Okay, so in some sense, this is not super surprising. Here we're just doing standard, bulk dynamics is related to anomalous dimensions. And so when this field has dimension 0, it just has some funny bulk evolution. And so that's the particular novelty here over just a so for fields for this calculation here, for a massive field, someone who's calculated these diagrams in ADS would recognize this calculation of an anomalous dimension or know some other way to do it that would reproduce this entire table. But the two novelties here that don't have an ADS parallel are, one, the stochastic inflation, which is coming because we have these operators of dimension 0. And the second is that when we go to talk about the principal series operators that have complex dimensions, those also don't have a nice ADS parallel. And there's a good reason for that, because both of these things would violate unitarity in a CFT with d greater than 2. And so these fundamental characters of what it means to be physics in de Sitter are breaking our sort of intuitive rules about the rules of CFTs, even though the representation theory all looks the same. So the representation theory looks familiar, but the rules will be very different because of these two properties that don't have a nice unitary equivalent. So in particular, what we're going to find, so the issue here is, okay, so you've broken the obvious rules of CFT. What are the rules that are left over? And so what we're going to do now is show that while it kind of makes sense that these things can have anomalous dimensions, they have to move to the right. That unitarity forbids negative anomalous dimensions for these principal series operators in a way that would, again, I don't know how to even prove this statement directly in terms of the de Sitter calculation, but we'll see it's an inevitable conclusion of cosmology. Okay, maybe I'll pause. Are there questions at this stage?
So at the moment, this real of gamma larger equal to 0 is just something we would like to happen, but we don't have an argument or derivation for.
So prior to now, there were arguments, but the arguments were kind of, let's say, if you had found that it wasn't true in a calculation, it would be very easy to point out where the argument was wrong, because it was basically made a lot of assumptions. And assumptions that are just like analytic properties. It's the same as saying, I assume blah is true, that this function is analytic in the upper half plane or something, but without any actual reason for doing that, making that assumption. It's just, if I make this assumption then, but the assumptions were not derived from any physical principle. Does that make sense?
Yeah.
So I think one way to state it was that there was an argument that said, if I think that I should always close contour integrals along this line to the right, and a state crossed to the left, then it looks like that state went missing and therefore violates unitarity. However, you already need to deform the contour to pick up any complementary series operators. So the resolution of saying, no, you just deform the contour when that happens would have been perfectly fine and consistent with the fact that complementary series operators exist. And so it's just kind of things like that. But however, most of the time it was just assumed. It was like, if it was true, then we can prove various results. But it was not known why it was true. Okay, so our strategy is going to be similar to some other ways that people have tried to understand the influence of unitarity in theories that we don't understand very well, which is to take a theory we don't understand very well, weakly couple it to something we do understand very well, and then like scatter stuff off of it, for example. So this is how, for example, people have put bounds on CFTs using the idea of deep inelastic scattering, where deep inelastic scattering, of course, was the experimental version of this, where we take electrons, which we understand very well, smash them into nucleus, which we didn't understand very well, and look what happens to the electrons coming out. But of course, we could do the same thing with, we did the same thing with CFTs. We wanted to understand bounds on CFTs by weakly coupling the CFT to some probe and demanding that the scattering of that probe particle is unitary. So here we're going to do the same thing. We're going to imagine these particles are present during inflation and are very weakly coupled to the metric fluctuations. So, or whatever, we could even couple them to a scalar that then at late times generates a density fluctuation. So the key idea is only that we have some intermediate particle that's coupled to the thing that we're going to observe in the sky. So it's going to we're going to couple the thing that we're trying to understand to the thing that we believe makes the density fluctuations of the CMB or the formation of galaxies, et cetera. So here idea, we're going to imagine this thing is present during inflation, and then we're going to ask, if that thing was present during inflation, how would it change the statistics of these totally classical things that we see in the universe? So just a lightning reminder of inflation, I'll try to get us back on time. So remember, so in the principle of inflation, so the standard picture of inflation is something like a ball rolling down a hill. We have the inflaton is evolving on top of a potential energy dominated potential up until some time when it rolls off the edge and then reheats the universe. And the role of this fluctuation of these scalar fields is to change how long inflation lasts from point to point. So we should really think of this scalar field as like a clock. And so the reason it gives rise to density fluctuations is the amount in which energy densities have been diluted from place to place are affected by how long inflation lasted. So we can think of this like the scalar field fluctuating up or fluctuating down and thus being closer or further away from the end of inflation, just locally changing the scale factor. Now, That local change to the scale factor we usually call an adiabatic fluctuation, and we describe it in terms of this variable zeta. And one way to think of this variable zeta is that it's just h times the relative amount of time that it took inflation to last in any given point. In this way, we can think of like kind of all models of inflation as just a theory of some kind of clock that sets the length of inflation, and the fluctuations of the metric are just related to the RMS fluctuations of the clock, which are some ratio of the Hubble scale to some high energy scale, which so we think of as like the ticks of the clock, or how precise our gears are. And so all of the fluctuations of this scalar field are controlled by a ratio of these scales, where f pi is always taken to be very large. So then we can think of the statistics of the CMB as just being statistics of this clock on the sky. So when we see temperature fluctuations at different points, they're just reflecting this underlying scalar metric fluctuation. Now, what's interesting is when you couple the metric to these extra degrees of freedom, even though the extra degrees of freedom are long gone by the time we observe them, the metric remembers their influence on how long it influenced inflation. And we can read off the couplings, the masses, and the spins of these particles from measuring the precise measurements of the statistics of the metric fluctuations, both in the CMB and in terms of the distribution of objects in the universe. So for example, we can imagine just taking this adiabatic fluctuation, we'll call zeta, and just taking some operator that lives in some part of our theory. We'll just think of this the same as some operator in a CFT. It's some operator that's defined, that's separate from the inflaton and separate from inflation, but it's weakly coupled through some derivative operators. This operator then can influence the statistics of zeta through, let's say, in a 3-point function via a diagram like this, or a 4-point function via sort of a classic exchange of this potentially heavy operator. Now, one way to think about what this operator does is that it changes the variance of this field. So if we think of this as the kinetic term for this scalar fluctuation, then this operator is modulating the constant in front of the scalar fluctuation, which is what sets the amplitude of the fluctuations. And so, for example, we could just think in a very like classical sense that the presence of this extra operator, if I have like random fluctuations of this scalar field, of this field zeta, then depending on the value of the scalar field, the variance can go up or down. So in this case, I've chosen the signs. So when this field is negative, the variance gets small. And so this is the influence of the operator O on this variable zeta. Now, in particular, because of that, we can actually read off more than just the coupling, but actually the scaling dimensions of these operators. So in particular, if I take this 3-point function and I look at in sort of configuration space where the two operators on the right are very far from the operator on the left, or said differently, that the momentum flowing through the middle of this diagram is very small, then the scaling behavior of that limit is directly determined by the dimension of the operator. So this is a tool that cosmologists have known about for a long time, where we can imagine actually measuring the spectrum of operators or the spectrum of particles present during inflation through their influence on the statistics. Okay, so now you know this fact about the 4-point function and the 3-point function. And now we can say, look, what we're talking about is just the influence of some stuff that was around during inflation, but is long gone. And what we're really just talking about is the classical density fluctuations of the late universe. Okay, so the classical density fluctuations, they have to obey classical information positivity bounds. So for example, they have to obey the Cauchy-Schwarz inequality. So if I take a composite object, we'll just call the power spectrum of zeta, and I calculate the 2-point function of zeta and the 2-point function of the power spectrum of zeta, that has to be greater than the cross correlation squared. Okay, this is just standard Cauchy-Schwarz. This is some object that has to be positive. This is some object that has to be positive, and this cross correlation is bounded to lie in between their 2-point functions. This is, again, just a statement that the correlation between zeta and its power spectrum has a correlation coefficient between -1 and 1. Okay, so if I take Cauchy-Schwarz and I interpret it as diagrams, it's a statement that the exchange diagram plus the disconnected Gaussian two-point function. So the 4-point function, which is showing up here, is greater than or equal to the correlation, the cross correlation, which is the 3-point function squared. Now, this thing was known for a long time. In the case where the scaling dimension, this delta, is related to the one from a massless particle, so delta equals 0 in this case, then the Gaussian term isn't important. The long wavelength correlator dominates, and so it just becomes 4-point is greater than 3-point squared. So this is kind of a trivial positivity bound on the coefficient of the 4-point function. This can be extended to other masses in the complementary series in exactly the same way. So any operator in the complementary series, again, you follow the same thing. The long wavelength behavior dominates as long as you're in the complementary series, and you can ignore the Gaussian piece and again derive that the 4-point is greater than the 3-point squared. Okay, so now we go to complex dimensions. Now, complex dimensions are very strange. So complex dimension operators can have, so we now are going to couple to some complex dimension plus the complex conjugate, so we have some real coupling. The 2-point functions between complex dimension operators has 2 possible terms. The first term is our standard favorite, the 2 times the dimension of the operators for separated points. But there can also be a contact term when the dimensions of the operator, the dimensions of these 2 operators add up to the dimension of space. So in this case, delta plus delta prime is equal to d. So in the case when we have the real part of delta is not equal to 3/2, so we have an anomalous dimension, the second term is absent. It can't be there. In addition, when we take the operator and its complex conjugate, it also can't be there. And so you get that this 2-point function is 0. This is particularly strange because this looks like the absolute value squared of something has a 0 correlator. The consequence of that is that the 4-point function does not have definite sign. It becomes this to a complex power plus its complex conjugate, which is an oscillatory term. So your 4-point function is purely oscillatory, but you have this contact term from the Gaussian theory to save you, just this 2-point function, these 2 terms to save you. However, if the anomalous dimension was negative, the long distance behavior would win. You could completely drop this term, and then you get a non-positive 4-point function, which is inconsistent with unitarity. Oops. Okay. And so therefore you conclude that anomalous dimensions have to be positive. Otherwise you'd have trivial violation of like just positivity of classical 4-point functions as demanded by Fisher information. And so just on those grounds, you know that they have to move to the right in this way. Otherwise you could couple them to sort of any weakly coupled metric fluctuation and generate impossible correlators that we would just go and measure and find like they don't even make sense. So this was argued based on this calculation of Marlff and Morrison along the lines of what was also done in ADS to be related to flat space unitarity. So for them, they argued, okay, look, the way that they calculate this anomalous dimension is actually by resumming a series of bubble diagrams. In the flat space limit, this resummation of bubble diagrams looks like a finite width. And they interpret this positivity of the anomalous dimension as being the same statement that the decay widths have to be positive in the flat space limit. This has been argued that this analogy is precise and that it works, but these are just arguments. Now you can extend this not just to DS. So in de Sitter, I use the full de Sitter isometry. So here I use the fact that this is conformal to require that you could only have like dimension operators or the contact term. In inflation, you can break the de Sitter isometries and you can allow yourself to have 2-point functions between operators of different dimensions. But so instead, this positivity bound puts an upper bound on the cross correlation between the operator and its complex conjugate relative to the absolute value of the coefficients of the individual 2-point functions. So you have either option. Either you have to have a positive anomalous dimensions, or this coefficient has to be bigger than the other two so that it retains a positive 4-point function.
Sorry, can I ask a quick question?
Yep.
So positivity here comes from the fact that you want to say something is a probability distribution.
Correct.
What is the thing that's probability distribution? I'm kind of confused.
So the probability distribution is not for our operator, but it's for the scalar metric fluctuation. So we calculate these correlation functions during inflation, and then we just wait until the universe is completely classical. And now we go and measure those correlation functions. Now we can prove that the probability distributions for zeta become classical. Like that is a fact that is provable in perturbation theory. Like if you want, we can say, look, we just take for granted that we know that in the late universe, we can wait forever to calculate these things, right? We're literally going to just calculate a statistical correlator of something like literally galaxies. We'll see in the next section that we can literally take galaxies and calculate the 4-point function of galaxies and recover the same result. And so you're really just doing classical physics in that regard.
So basically the assumption is, or maybe the argument is that there is a probability distribution, there's a probability measure on the space of zetas, right, at late times.
Yes.
Okay. And then because it's a probability distribution, you're getting all sorts of inequalities. I see.
So yeah, but I'll maybe make it again. I realize I'm probably running out of time, so maybe I can give you a punchline since you have to teach, right?
It's all right. No. It's the semester has ended, so feel free.
Okay. Okay. Maybe this is a useful point to give some sort of more concrete intuition for why. Because at face value, you might think, how can you just derive anything interesting from a trivial statement about Cauchy-Schwarz of a classical variable? And the reason is the following. Sorry, let me find the statement here. Okay, so the reason is that the positivity of these operators in de Sitter is not obvious at all, right? Like these operators do not obey positivity, and it seems problematic. Like you have these operators that don't have, this is like an absolute value squared that's equal to 0, but it has two non-zero 2-point functions. So the problem is like this operator seemed problematic on its own. And your question was, well, if I just work in de Sitter, I can't prove purely in de Sitter that that's a problem because I don't totally know the rule. So for example, you would if this operator could create a state, this statement here is that the statement has 0 norm. And so if there was a state order operator correspondence, this would immediately tell you that the theory was not unitary. But there is no state operator correspondence because this would be true for either side of gamma. It doesn't actually matter if gamma is positive or negative. Any gamma not equal to 0 eliminates the fact that this could create a state that has a unit norm or any norm. The norm is 0 for this operator. So it can't create a state. And so that is confusing and hopefully makes you not terribly happy. And so, but the question is that a problem? It certainly seems to be a property of things we can directly calculate. And so your question is, I can't prove in an easy way that this is a disaster for de Sitter itself, but what I can prove is that this anomalous dimension is negative, that if I weakly couple it to something that makes total sense, a classical statistical variable, then I will get correlations that don't make sense in the context of classical statistics. Does that make sense?
Yeah, can I say these words and see if you agree with them? There is no way of constructing a Hilbert space here because as we usually do in local physics, where there are local operators that act on a state and create excitations, and that's a vector space, there's an inner product, all of that. That structure is not present here. What is present is a set of correlation functions with a bunch of positivity properties.
Correct. Correct.
There's no.
Yeah. So now what people will do is they'll say that they will create a Hilbert space, and they'll say that they can insert so in this correlator, they will say I can insert the identity and I can construct a density of states associated with this operator. And what it does is, so the states all live along this line. And you construct, so for a single operator, take this operator, I act on this complete set of states, it creates a continuous density distribution of these states. Now, if I look at the density of states and I analytically continue it, I will see a pole at this spot corresponding to this operator. So the sense in which this insertion of a complete set of states is useful is only through its analytic structure remembering the origin of the operators. But the states all live along this line and the operators all live to the right of this line. And so the relationship between the dimensions of states and dimensions of operators is completely broken, except when you analytically continue the density of states. Does that make sense?
Yes, there's one more thing I wanted to say. So in Euclidean CFDs, we're also dealing with complex dimensions, right? If it's non-unitary CFDs.
Correct.
But we still have a path integral picture. Here we don't have a path integral picture, or do you
Correct.
have?
No. It's the same issue, because complex dimensions in principle are okay, but here the issue is that we don't really know the rules in any good sense, right? This is why DSCFT has been so unhelpful, is that it's not just not unitary.
It's a collection of correlation functions with a bunch of nice properties under the conformal group. Basically, that's what we have.
Correct. And to the degree that things like the wave function have been useful or DSC have been useful are just nice ways of organizing the symmetry properties of those correlators. But beyond that, no. And so in general, that is the sort of interesting thing, is that we've made a lot of progress understanding the correlators and thinking of the correlators in a very field theoretic sense. But it has these, again, this example being a good one where even within those set of rules, we don't there's surprising facts that you're I really it. It's not obvious that you should be allowed to have complex dimensions that then have this structure where 2-point functions of things that look real are clearly not positive. That just doesn't make me happy at all. But yeah, I mean, okay, maybe I'll spend 5 minutes going to the observational stuff and then we can stop there. Does that sound reasonable?
Yes.
Okay. Okay, so one of the things that's nice about the subject, this subject as a whole, is that there's a nice connection between the formal and the observational. They're really, unlike a lot of other subjects where there's a lot of, there's a lot of bureaucracy that works very hard to make it hard to connect your ideas to observations. Here it's really in your face. And so one of the things that's really happening right now in observational cosmology is the movement from the CMB to large-scale structures being sort of the dominant tool for understanding inflation, for example. The reason it's useful is just because the CMB is kind of a two-dimensional observable. So if you think of it as a bunch of pixels, then the amount of information that encodes the amount of information is how many pixels there are in the sky. And so roughly speaking, the number of pixels in the CMB is the smallest size you can resolve divided by the biggest size you can resolve squared, because it's two-dimensional. In large-scale structure, it's a three-dimensional map of the universe. And so it's still a ratio of the smallest scale you can resolve divided by the biggest scale you can resolve, but now it's cubed. And so as a result, even if you are looking at the same range of scales, which are kind of roughly similar, here are different observables all plotted on the same map, you just get this extra power, which means that in the long run, you're always going to win by having three-dimensional information. Now, the challenge is that the late universe is messy, and so there's all kinds of nonlinear structures you have to deal with. And so the trade-off between more information and potentially less useful information is a big problem that this subject faces. Now, there's a thing that's very nice in our understanding of galaxies. So here I'm going to quickly define a thing called bias. So bias is, the name is kind of not helpful. It's the dumbest possible thing you could imagine. So as sort of lazy theorists, you would stumble upon bias even if you didn't know what it is. So you say, look, I want to know how many galaxies are in this part of space. And you say, well, I don't know anything about galaxy formation, but it probably depends on how much stuff there is in that part of space, plus, stuff roughly around it. So presumably it's some local function of the matter and derivatives, etc. And so, okay, it's some function you don't know. I have a function I don't know, but the arguments of that function are small. What do? I Taylor expand that function. And so you get that your guess for where galaxies are is that they're roughly correlated with where the matter is, plus the matter squared, plus an infinite series of operators that is just the Taylor expansion of some unknown function. And these coefficients, called the bias parameters, are some unknown things. And so in general, this is just a different way of representing some function that you presume is local in space, or local-ish, local enough that galaxies formed here don't depend on what's happening on the other side of the universe. Okay, so one way that people have derived a specific function for this expression is through the following sort of...
Can I ask
Yep.
a silly question?
Go for it.
Naive theorists would have just included a bunch of derivatives here.
Yes, the derivatives are there. They're just,
Oh,
I've dropped them here. The derivatives
Oh.
are definitely there. Absolutely. They're just, in our case, it won't matter, but they are included in the analysis, et cetera. It's just that derivatives tend to be dominated by smaller scales. And we're going to be interested in what happens on larger scales. But absolutely, there's derivatives. And in fact, I've also cheated you because there's technically tidal tensor terms that are consistent with the, that are allowed and don't take the form of the matter density. And people also include those. And that was all described in this paper by McDonald. I dropped the D in 2009. Okay, one sort of conceptual picture that people like, though, for where this function comes from and can be used to sort of give a model that's not so bad is through this idea of critical collapse. So in this critical collapse model, you think of galaxies as forming at the sort of the rare peaks. So there's like density fluctuations everywhere, but when the density fluctuations are big enough, they collapse into like kind of nonlinear objects and then they form galaxies inside. And so in this case, the relationship between where galaxies are and the sort of long wavelength matter is that if I have this kind of like random short wavelength noise, but then I put that on top of a long wavelength fluctuation, then at the peaks of the long wavelength fluctuation, I'm just closer to the barrier. So it's just easier to find myself above the critical barrier when this thing is high than when this thing is low. Okay, and that gives rise, that sort of preference for pushing this thing up gives this coefficient B1, which relates the sort of proportionality between the very long wavelength matter fluctuations and the very long wavelength presence of galaxies. But the fact this number isn't 1 is because of this fact, because it's a threshold. So you're much more likely to form galaxies at the height, at the maxima, than you are at the minima. Now, this feeds directly back, literally, this is exactly how people think of how primordial non-Gaussianity influences galaxies. So remember, if I took that operator of dimension delta and I coupled it to the inflaton, it didn't change, it changed the variance of the fluctuations, whether I was at the minimum or maximum of this long wavelength operator. So now what happens is when this operator is I'm at its peak, I just think of Fourier transforming the classical solutions equation of motion, then when I'm here, I'll find myself more likely to make galaxies because the variance is higher than when I'm at the minimum, because the variance is smaller. Now, this is interesting because what it does is this introduces an effect that looks non-local as far as Newtonian physics goes. Because the way that this effect shows up is inversely proportional to the wave number when the dimension delta is not equal to 2. So when delta is like 3/2 or 0, this looks like 1 over k squared. And it's because it's an operator and not a gradient of an operator coupling to the long and short modes. And so what happens is that this changes the distribution of matter and the distribution of galaxies at very long distances, far away from all the ugly nonlinear stuff. And so we can measure the spectrum of these operators by looking for these kinds of tails at long distances, where this growth of power at long distances is directly related to the dimension of the operator that couples to the inflaton. Now you can literally look for this. So here's an analysis we did, trying to put constraints on the coupling of operators of dimension here between 0 and 2 to the inflaton. The constraints get better at low delta for precisely the reason that that's where this effect at large distances becomes much bigger. This is also kind of how people are going to look for non-Gaussian in the future, and it's really the motivation for surveys like SphereX that are looking for like multi-field inflation effects in large-scale structure. Okay, and it's also in these future surveys part of our plans. Okay, so let's see. I'm gonna just jump to the other part. So the key exciting thing is that using this tool, you can really push future limits beyond Planck, and so it's really like part of the core mission because this non-local effect is easy to measure, doesn't deal with all of this crap of astrophysics on small scales, and allows you to do better than Planck for some decent region of operator dimensions. Okay, as stated before, I just wanted to conclude with the funny fact that this exact observable has these positivity properties built into it. So specifically, again, we can just do Cauchy-Schwarz at the level of the matter in the galaxy. So the power spectrum of matter times the power spectrum of galaxies is greater than or equal to the absolute value squared of the cross correlation of galaxies and matter. Now, if I take these 4-point functions or 3-point functions that everyone's looking for that give these kinds of signals, and you just plug it into this expression, you get this classic this tau and L minus FL squared 4-point function minus 3-point function squared coefficient. When delta is sufficiently small, this is the result we had before. But now, interestingly, there's even a bound. There's a bound when delta's exactly on the line, 3/2. That previously we just had a bound like this, that this was greater than this one here. This would have been a previous bound in the case that the dimension delta is equal to 3/2. So when it's less than 3/2, this wins, and then it's F tau and L greater than F and L squared. But when it's equal to 3/2, then you have a bound. You can compare this bound to the one from galaxies. And the role of this term here, which is the disconnected 4-point function, is played by the total number of galaxies in the universe. It sets the shot noise of this experiment. And so by demanding that the bound that you derive from directly measuring all of the modes in the entire universe has to be stronger than the bound you get from measuring galaxies, you place an upper limit on how many galaxies can form in this model, or in the universe. And so you can take it the other way. Rather than using positivity to prove things about inflation, you can also use the same argument to prove things about the number of galaxies in the universe. And you can look at it from either perspective. So this is, again, just another funny, this is a completely trivial statement, but somehow combining two completely trivial statements gave you a non-trivial statement about how many galaxies there are. Okay, so just to conclude, so what we looked at was how to think about the fluctuations of inflation in terms of a spectrum of operators and their dimensions. This allowed us to make sense of some peculiar things like stochastic inflation that seemed to come out of nowhere. And it gives hints at some deeper structure of our understanding of de Sitter in terms of the potential for positivity bounds and hopefully like real rules for what these statistical correlators have to obey. Interestingly, the same way we're thinking about these operators just from the pure, like, how do I understand de Sitter space quantum mechanically, leads to interesting ways of thinking about observables and ultimately can put interesting rules on the kinds of things we can look for in upcoming surveys. Okay, I'll stop there. Thank you. And again, sorry for going long.
Thank you so much. Are there any questions? Maybe from the online people?
Let me make sure I'm not missing any.
I have a question. So you talked a lot about the equal time correlator at late times.
Mm-hmm.
But you didn't talk much about phi 0, phi t, 2-point function as you separate the observables in time.
Yeah, those are not, so purely separated in time, I think is straightforward. It's just it'll follow the same dimensional scaling. So I focus on equal time because for the positivity, because that's the one where you know the equal times have to obey sort of positivity constraints that the not equal times don't. Because they're not like if in the random walkie picture even, right? Like one of them has modes that are not included in the other. So there are certain rules. So the correlation functions in time and in space can be solved using the stochastic inflation framework for the light scalars. We can also solve it for the we can also do it for the not light scalars in perturbation theory. I guess what I would say is I haven't seen a case where we have gained a lot of insight from that, but there has been interesting work there's interesting work in global de Sitter where you try to use like correlations between the past and the future to try to say something interesting. So when you do not equal times in that context, like you can construct something that kind of looks like these kind of shockwave bounds or these like light ray bounds, because you basically can take operators that are outside the light cone and bring them together.
Yeah.
In the cosmological slicing, where you're kind of like looking at stuff that's kind of all separated, making slightly different times is not very helpful because they're still all space like separated.
Right.
So you really, the only situation in which you're helpful is kind of like along one world line, doing correlators along a world line. And so that one, I would say, I guess I would say that that we know how to solve those, but I haven't seen any insight that was different than what I said in terms of like getting back to this differential equation, right? Or just knowing the spectrum of operators. That once you know the dimensions of the operators, that the time evolution for that kind of object just follows from scaling behavior. So, but that's not to say that there aren't interesting cases. I'm just not aware of how you would use it in this particular context.
I see. Thank you so much. Any other questions? If not, let's thank Dan again.
Thanks everyone for your time.
Thank you so very much, Dan.
My pleasure. Great to see you all.
Great seeing you, and have a good, I guess, rest of your week.
Thanks. I'm still teaching. I'm envious of you that are finished with
Oh,
course.
we finished last. I finished last.